In this video homework guide, I will cover some of the main ideas when you're being asked to sketch the graph for a variety of different functions. Before I start this video homework guide, I won't be going over all the algebraic steps to find like the first derivative and the second derivative. I'm simply going to give you that information, and we're going to use that information to sketch the graph. I also just want to say that based on the kind of graphs you have, every single graph may have a slightly different kind of a technique or approach in order to finish off the problem. Now, when you're asked to sketch graphs, I would go ahead and find the Y-intercept first if you can. So the Y-intercept happens when the x value is equal to 0. And if I plug in 0 for here, that's the same thing as e to the power of 0. Which is going to be 1. So the y-intercept is 0, 1, so you can find that right away. And then after that, this is where I'm going to skip some of the algebraic steps, and I will go ahead and give you the results from the first derivative test. So this is my first derivative, and your critical number here is going to be 0, and the sign goes like this, positive on the left-hand side and negative on the left-hand side. Or sorry, positive on the left-hand side and negative on the right-hand side. So that means you have a maximum when x equals to 0. So step number 2, let's go ahead and find that, that critical point there. So if I plug in 0 here, let's go ahead and plug in 0 back into the original function there. So if I do that, I will have e to the power 0, and e to the power 0 is 1. Okay, so it turns out that our y-intercept is going to be a maximum. So this right here is a max. Okay, after that, I'm going to kind of skip ahead again, and I want to give you the results from the second derivative. And from the second derivative, there's an x value of negative 1 over root 2 and an x value of positive 1 over root 2. And the results go from positive here on the far left-hand side to negative in the middle and positive on the right-hand side there. Okay, so what that means is you should have an inflection point here and an inflection point here, and then after that we should go ahead and find the actual coordinates. So so step 3, let's go ahead and find the inflection points. So the x values will be 1 over root 2, and if I plug in 1 over root 2 back into this original function here, the corresponding y value will be 1 over root e. So these are things that you should definitely be able to do. I won't be spending the entire time in this video going over each step here. What I really want to do is I want to use the results and then put all the results together so that we can actually graph the function here. So this is negative 1 over root 2, and if I plug that back into the original function, I should get 1 over root e. Okay, so all this information that I'm giving you right now, you should definitely make sure that you can do this on your own, and we've done quite a bit of practice with these kind of steps in a lot of the previous homework problems, and I simply just want to summarize the main results now. Okay, so let's go ahead and graph this. So here's my xy axis. We'll do our very best to sketch this. Maybe I'll draw my x-axis a little bit lower here. Okay, so maybe the very first thing you should do is you should go ahead and plot your y-intercept and your maximum here. It seems like the y-intercept and the local max there, or the absolute max in this case, are the same point. So let's put a point right here. This is the point 0, 1. And then let's go ahead and plug in our inflection points. So our inflection points are here, steps 3 and 4. So roughly those points are about here and there. So this is going to be 1 over root 2, 1 over root e, and this will be negative 1 over root 2, 1 over root e. And remember, our y-intercept has a maximum, right? So it's at the y-intercept, you should definitely kind of curve it out because it is a max, right? So we do have a max here, so that's how we should kind of create the graph with that kind of shape. And the max will definitely move on, and it will definitely connect with this point here, and it will definitely connect with that point there because the inflection points are points on the graph. Now for this particular problem, you have to ask yourself, what's happening if I go forever to the right hand side and forever to the left hand side? That's something that you need to consider now because we need to complete this. So what you could do is you could set up a limit statement. The limit as x approaches infinity of the function e to the power of negative x squared. Now, because there's a negative exponent here, you could rewrite that as e over x squared, and then I can erase that. And then the key thing here is, regardless if you're going to positive or negative infinity, regardless if you're going to positive or negative infinity, if you plug that into the denominator, your result will be e over infinity, and e over infinity is going to be 0. So as you go forever to the left or the right, the height that you approach is actually going to be 0. So what that means is the graph is just going to level off like this, and it's going to be very it's going to approach the x-axis but not touch it. So it's going to level off like that. Okay, so that's what the graph would look like once you kind of have all the results and you can plot it. One more thing you can do is you can verify your results here. So here's my first derivative test here in blue. If I just draw a number line underneath this, and I have my critical number at x equals to 0, and remember I gave you these results when the question first started here, and it was positive on the left hand side and negative on the right hand side. And you can verify that it actually works, right? So we have a positive slope here. All of this is positive. And when you have a negative slope, all of this is negative. So those results actually work quite well. Okay, let me just erase that. And after you're done that, you could also verify the results from your second derivative test, or the results from the second derivative. And if I draw another number line here, this would be negative 1 over root 2. This would be 1 over root 2 here, or positive 1 over root 2. And over here it's positive, meaning it's concave up. And in the middle it's negative, which is concave down. And clearly, and this one's pretty obvious, that's concave down from there to there. And then it's concave up as you go to positive infinity, or the right hand side of 1 over root 2. And hopefully that makes sense, because concave up, when you have a CU concave up, a concave up graph looks like this. Okay, and basically the concavity here is so this part of the concave graph, this blue part right here represents that part right there. So that's the concave up there, and this concave up right here, this green part, represents that part of the graph right there. So as you can see, the results all do indeed line up, and that's how you can check your answer at the very end there. Okay, so let me just erase all this. That was just kind of for some extra learning there. And anyways, this is your answer right there. Okay, so once again, for these particular problems, I'm not going to go over all the algebra work. Instead, I'm going to give you the results from the first derivative test, the inflection points, and some other key points, and then we'll try our best to use that information and sketch the graph. Okay, let's move on to the next question here. I need to sketch the graph of this particular function. Step 1, I would go ahead and find the y-intercept, which was very similar to the previous problem. So the y-intercept happens when x equals to 0. And if x equals to 0, if I plug in 0 here, then the y value has to be 0. So that's step number 1, to find the y-intercept right away. And then for step number 2, I will once again give you the results from the first derivative test. So this would be y prime, and the critical number that I have here is going to be 1. And it's going to be positive on the left hand side, and then it's going to be negative on the right hand side, and that means we have a maximum right here. Okay, so once we know that we have a max when x equals to 1, I would go ahead and find that coordinate there. So on the original graph, when x equals to 1, what is the corresponding height? Well, that means we plug in 1 over there, so that would be 4 times 1 times e to the power of negative 1, which equals to 4 over e. So this would be 4 over e. And what that means is this particular point now, that's your max, right? So you have a max at the point 1 comma 4 over e. Okay, and after that, I will give you the results from the concavity test here, or when you're taking the second derivative. And This will be 2 here, and it's going to be negative on the left-hand side and positive on the right-hand side. And that means we have an inflection point right here. We're concave down to the left of 2 and concave up to the right of 2. And after that, let's go ahead and find the actual inflection point. So the x value is 2. And then if I plug in 2 back into here, it's going to be 4 times 2 divided by e to the power of e to the power 2. So that's going to be 8 over e squared. So 8 over e squared. Okay, so this right here would be my inflection point. Okay, so if we're given this information here, the goal is how can I take all of this and produce a general sketch of the graph. Okay, so let's go ahead and draw the xy axes here. And step number 1 is let's go ahead and plot the y-intercept. That one's probably the easiest thing to do. So the y-intercept is right there. And then after that, let's go ahead and plot the maximum point here, which is 1, 4 divided by e. That's about, 1's about here. And 4 over e is going to be roughly somewhere up here. So let's label that as 1, 4 over e. And because it's a max, you should definitely level it off like that because it's a max. And then we have our inflection point, which is 2, 8 over e squared. And I guess 2 is about here. And the point 8 over e squared is slightly lower. So it would be 2, 8 over e squared. And I know that this is probably going to connect to that inflection point. And I know that this part of the graph has to, hit the y-intercept here. So let's do that. Okay, so there's a general little sketch right there of what's happening. And then you have to ask yourself, well, what's happening to the graph as I go forever to the right? Here is forever to the right. And what's happening to the graph when I go forever to the left? All right, so the kind of calculus that you need to know now is computing limits now. So we have to take the limit as x goes to infinity and x goes to negative infinity to determine how the end behavior is working for this particular graph. Okay, so I know the original function was 4x times e to the power negative x. So let's go ahead and do a limit calculation here. What's the limit as x goes to positive infinity? Okay, one way you could do a particular problem like this is you can look at the 4x and you can look at the e to the negative x separately. I know if I plug in infinity for here, that's going to give me an infinity result. But what happens if I plug infinity for this graph there? Well, if I take a look at the graph at e to the negative x, this graph isn't too hard to figure out. If you do a light sketch of that particular graph, the graph will look like this. So ask yourself, what's happening if I go to positive infinity? Well, that means the graph at e to the negative x approaches a height of 0. So I can take this 0 height and plug it in over here. So infinity times 0 is going to be 0. So what that means is if I go forever to the right-hand side, the graph levels off to a height of 0, like that. Okay, and that's how you can finish off that part of the graph. And then what we need to do next is let's figure out what's happening to the graph as I go forever to the left-hand side. So that means I need to do another limit statement. That's the limit as x goes to negative infinity of the function 4x e to the power of negative x. Okay, so once again, we can look at both of these functions separately if that helps. And I know if I plug in infinity for this expression, 4 times negative infinity is going to be negative infinity. And then for for this part of the graph, I can go ahead and use my reference graph right here. And if I go to negative infinity over here, what's happening to the height? Well, if I go to a negative infinity, it's going to a height of positive infinity right here. So this is going to be infinity times negative infinity. And if I take this result here, that's going to be negative infinity, right? So what that means is if I go forever to the left-hand side, the graph is going to negative infinity. So negative infinity is going downwards like that. So 1 second, it's going downwards like that. So this would be going to negative infinity there. So this would be my graph right there. Okay, so that was quite a bit of work to get that graph done. What you could do to kind of finish off this particular problem, let me just kind of erase that part. You could do a number line check to just verify that your results are correct. Remember, my first derivative happened when I have a critical number of 1, and it was positive on the left-hand side and negative on the right-hand side, and you can see that the results do match up. To the left of 1, this is all a positive slope, and then all of this is roughly a negative slope like that, going downwards. So the results there do look right. And if I go ahead and just do the second derivative, concavity now, let's go ahead and put the results for the second derivative here. I believe the numbers were 2, and it was concave up to the right hand side, and that looks right to me because concave up looks like this, right? And you can see that this part of the graph, this part's concave up, which represents that part of the graph roughly. And on the left hand side here, we know it's concave down here. And that's about right too, because concave down looks like that. And this purple part, that's the concave down part, which is this part right there. So the results look relatively right. Okay, let's move on to another graph here. Next question here. The next one is a logarithmic question. Okay, let's move on to the next one. For the next graph, I need to sketch y equals to ln of x squared plus 1. So for this particular problem, I would start off by finding the y-intercept, and that happens when x equals to 0. And if I plug that in, if I have ln of 0 plus 1, that's the same thing as ln 1, and ln 1 equals to 0. So my y-intercept for this particular problem is 0, 0. And then for the second part, I will give you the results from the first derivative test. And there's a critical number of 0 here, and then it's negative on this side and positive on that side. And because of that, we do have a minimum at x equals to 0. Okay, well, since we know what the y value is when x equals to 0, the point 0, 0 is the y-intercept, and it also represents a minimum point. Okay, third step here, I will give you the results after working with the second derivative, and the values I have here are now -1 and +1, and the results would be negative in this region, positive in this region, and negative in this region. And that means you have an inflection point here and an inflection point there. Okay, so my fourth step here would be if I'm given the x values of 1 and -1, let's go ahead and find the corresponding y values because those represent the inflection points. So if x equals to 1, I would be given a y value of ln 2, and if x equals to -1, I have a y value of ln 2 as well. Okay, so once again, the purpose of this video is not to go through all the algebra to find these results. The purpose of this video is to use the results and create a general sketch of the graph. Okay, so let's go ahead and draw x-y axes here. My first step would be to plot the y-intercept, which is at the point 0, 0. And because it's a minimum, you should definitely start making it look like a minimum like that. And then let's go ahead and plot the inflection points next. So 1, ln 2, so let's just say this is 1. So that point there could be 1, ln 2. And then if I line that up to the other side here, let's just say this point right here is -1, ln 2. Okay, and then let's go ahead and just continue the sketch here. Alright, so that's what the graph kind of looks like right now. And then you should ask yourself, well, what's happening to the graph as I go forever to the right-hand side and forever to the left-hand side? Now, in order to figure that out, you need to do a limit calculation. So let's do the limit as x goes to positive or negative infinity. And our original function here was ln of bracket x squared plus 1. Now, regardless if x is going to positive or negative infinity, if I plug that into here and if we square it, it's always going to be positive. So we really have ln of infinity plus 1, which is the same thing as ln infinity, and ln infinity is going to be infinity. So what that means is if I go forever to the left-hand side or the right-hand side, the graph is going to a height of positive infinity. So kind of like that, positive infinity and positive infinity like that. And that's roughly what I'll have for my final answer for the graph there, and it's not too hard to really check these results with the first and second derivative tests. Okay, let's move on to the last graph for this particular video. Okay, so I have a rational function here. Now, when you have a rational function here, you know, I would still go ahead and find the y-intercept. I mean, the y-intercept happens when x equals to 0. And if I plug into 0 into this problem here, I would get 0 on the top and 0 plus 1 on the bottom, which is going to be 0, 0 again, so 0, 0. You should also recognize that you do have a horizontal asymptote for this particular problem because it's a rational function. And since the denominator has a higher degree than the numerator, we know that the horizontal asymptote is going to be at y equals to 0. Okay, the third step here, I will give you the results from the first derivative test. So y prime, and my critical numbers are -1 and 1. And that means it's going to be a the results here would be negative over here, positive over here, and negative over here. And that means I have a minimum when x equals to -1 and a maximum at x equals to positive 1. So my fourth step here is let's go ahead and find the actual values, the actual coordinates when x equals to 1 and -1 by plugging those numbers back into the original. And if I do that, I would get 1 and 1 comma 1, so that's a max here. And for -1, I would get -1, and this is my minimum point here. Okay, the fifth step here, I will give you the results from the inflection points. So the x values here are going to be 0, -√3, and +√3. And the results go like this: negative to positive to negative to positive. And that means you have an inflection point here, here, and there. So you have 3 inflection points. So my sixth step here is I'm going to give you the actual coordinates of the inflection point. So if it's -√3, we plug that back into the original function, and I would get -√3 over 2 for the corresponding y. 0 is going to be 0, 0, and for +√3, my height would be √3 over 2. Okay, so we're going to use all these results here, and our goal is let's go ahead and sketch the graph now. Okay, so here's my x and y axes. Step number 1, let's go ahead and graph the y-intercept, which is at the point 0, 0. And let's go ahead and graph the maximum and minimum points next. So I have a maximum at 1, 1. So 1, 1, and a minimum at -1, so since there's a maximum, I'll draw it like that. And this is the point -1, -1. Okay, and after that, let's go ahead and plot the inflection point. So there's an inflection point at -3, -√3, -√3 over 2, and there's also an inflection point at √3, √3 over 2. So if I plot those points, this is going to be the point roughly √3 over √3 over 2, and then there's a point over here, which is -√3, -√3 over 2. And then let's go ahead and connect the dots here roughly. So that's going to connect like that and like that. Okay, so that's what we have there, and we know that there's a horizontal asymptote at y equals to 0. So what that means is the graph is going to level off like that and like that, and that should finish off the graph for that particular problem.